Alright, hello. This little recording is to answer some questions that a number of students had concerning Project 1. So what I'd first like to do is define the circular geometry that we're going to be working with. So here's a cylinder of two radiuses, and here's Fourier's equation, which gives the heat rate, which is proportional to the thermal conductivity, the area, which in this case is going to be given as 2 pi RL. Now let's hold on for a second. Again, the area is now going to be a function of the radius, and we also have the temperature, which is also as a function of the radius. So these both come into play when we are doing the derivation of our equation. So let's continue, and we need to figure out an expression for T as a function of R, and we get that from the heat equation. So as we solved in the previous homework, we have TR, so let's introduce our T inner and our T outer from the surfaces, and the temperature profile is going to be proportional to the temperatures and the natural logarithm of the radiuses. And again, notice in the equation, in the second logarithm, the numerator is just r. So again, that is the radial coordinate that runs in between the inner radius and the outer radius. Okay, so now we can rewrite the equation and put our parentheses around it, because what we're going to want to do now is take the derivative of this equation with respect to r. And when we do that, we can take it and we can plug it back into Fourier's equation. And once we've done that, this will now allow us to write Fourier's equation for a one-dimensional cylindrical geometry, and it is strictly in terms of the inner temperature, the outer temperature, and the inner and outer radiuses. And again, the 2 pi L, the 2 pi comes from the area of the cylinder, and the L will be now the length of the cylinder in and out of the paper. And once we've done that, we can then define a thermal resistance, which will be proportional to the thermal conductivity and the length and the radiuses of the cylinder. And once we do that, we can write a simplified equation for Fourier's equation, which again now is just equal to the temperature gradient and the thermal resistance. But notice that the thermal resistance is no longer linear like it was for the plane wall, but now it has a logarithmic, which will give us the curved feature in the temperature plots. Alright, moving on to the next slide. We again have our radiuses, but now what we're going to do is we're going to make it a composite wall. So we have two different layers, and now I'm going to define the temperatures as being T1, T2, and T3. Again, now our three radiuses, R1, R2, and R3. And now what I'm writing is I'm showing three arrows here, which are going to be the heat rate going through each of the layers. So the first one is QA, next one's QB, and the third one is Q. Now, I'm going to state it more in the equations, but what we're essentially saying is that if you have 60 watts going from the inner surface to the outer surface, it's 60 watts has to go from 1 to 2, and then that same 60 watts has to go from 2 to 3. So, as we said with the plane wall, QA equals QB, which equals Q. So now if we write QA, and we wrote Fourier's equation for it, we would find out that it's proportional to temperature T1 and temperature T2, R1, R2, and the thermal conductivity of A. Now we can write the same for B, and we find out that it is proportional to T2, T3, R2, R3, and KB. Now, if we think about this in terms of the problem that we're trying to solve, we typically would know the inner temperature T1 and the outer temperature T3, but we don't know what the temperature at the midplane is. And that is why we wouldn't know how to solve for the total Q until we recognize that now we have two equations and two unknowns. So if QA equals QB, which equals just the heat rate through the both cylinders. That gives me one unknown, and now this T2 is my second unknown. I can equate QA to QB, solve for T2, which now will be a function of T1 and T3, known quantities, R1, R2, and R3, which were known quantities, and Ka and Kb, which again would be known quantities. These would be the inputs to the program that you would be asking the user for. So now, once you have that, you now have Q, which is now a function of the known temperatures and the known thermal resistances, which again are just proportional to the thermal conductivities and the known radiuses. So now once you have that, you then can also, once you know the total temperature flowing through, the total heat rate, you can now come back and solve for your intermediate temperature, because now you know Q, you know T1, and the only thing that was unknown in your QA equation was the T2, so you can solve for that. So now we go through and we can make our plot, and here's T1, here's T2, and here's T3. And the only thing you have to do is you have to remember that the previous slide showed us that we have temperature R. The temperature is a function of the radius, has a coordinate R, and that's where you're getting these curved plots from. And I'm going to say here at the end that you are following the procedure that we already had done in Lecture 3 for the composite wall, or the composite plane wall. So hopefully these couple steps will take you through what you need to do in terms of setting up your analytical description. And basically what you're trying to do is make sure that you don't have a miracle occurs getting to this equation where you have the temperature, or rather the heat rate, going through the cylinder being proportional to the temperatures on the inner and outer walls of the composite cylinder divided by the sum of the individual resistances. Anyway, hope this helps, and if you have any questions, please send me an email over the weekend. Enjoy the snow.